Right, I guess we're live, are we?
Yep. Okay.
Okay, so welcome to the 0 to ASIC demo. I'm Matt Venn. Super.
1 second. Let me go through your bio. You took the time to write the bio, so give me a second to read it, and we'll go. Okay. Good.
Already messed it up. I'm too excited.
That's fine. Okay. Cool. Hello, everyone. As you heard a second ago, welcome to 0 to ASIC. Matt Venn has been doing some combination of electronics and teaching for most of his life. Most of the work he does is on the science communication spectrum. Some is straight electronic engineering, and some is explaining concepts on YouTube. A few years ago, he got into FPGAs, and more so after the open source Flow was released. Learning to create hardware inside FPGAs has been very interesting and given more insight on how all the microcontrollers he's used has actually worked. He still didn't really know what designing hardware with a language like Verilog actually ended up on a chip, though, so he started looking into the process and taking a few courses on VLSI. And I guess a few courses on VLSI leads us from 0 to ASIC. So without further ado, Matt, take it over.
Thanks. Thanks for the introduction. So yeah, I'm super happy to be here. It's quite a funny experience being part of a remote conference, but I'm really glad that Hackaday have done this, and I want to say thanks to the Hackaday team for extending out the kind of 20-minute demo slot into something that I can fit this into, because it's a bit of a huge subject. I'm really a learning by doing kind of person. So when I decided I wanted to learn a bit more about ASIC stuff, I just kind of jumped into doing the VLSI courses, doing magic stuff. And then there was this big announcement by Google and Skywater for this open source PDK. So one of the things I'm going to really try hard to do is to not confuse everyone with loads of jargon. So this really is a 0 to ASIC course. So let's start at the top. ASIC is a custom integrated circuit. So it's lots of tiny little switches packed into a silicon chip and then put onto a tiny little chip, and then you put that on your board. So the aims of this kind of 1-hour demo presentation is to give you a high-level understanding of what it takes to make a custom digital chip, why you might want to do that, see some of the tools in action for simple design, familiarity with the jargon, to kind of take away this slightly unapproachable aspect of ASIC stuff, and where to find help. And this is the kind of the flow that I'm going to follow through this presentation. So if you could, I'm going to paste this in the Twitch now, in the Twitch chat. If you could fill in the stuff that you're most interested in this walkthrough, then that will help me allocate the time to the stuff that people are most interested in. So I'm going to start off with like a little bit of historical context, talk about digital switches, look at how they are made and packed into these tiny chips, look at the Skywater factory's chip making specification. That's what the PDK is, process design kit. So that provides all the information you need to make a chip using that particular factory's process for the type of process that they've made open source. OpenLane is the name of the tool that we use to build the chip. A little bit of a look at digital design with a hardware description language and a bit of simulation and verification, and then ending up with Google's free chip manufacturing opportunity. So this is the one of the things that's most exciting about this is having the actual opportunity to make your own chips. So at the end of this demo, you should have seen the whole thing. If you want to do it, there's links in the resources, all the slides will be shared and so forth for you to get involved. So I'll just look at what the results are. And looks like it's fairly evenly spread. There's nothing that anyone's completely uninterested in, so I'll go at my kind of the pace that I've been practicing. Okay, so why is a good question. Why would you want to? I think this is going to be a really exciting field. We've seen how open source has kind of revolutionized different technologies, and we've kind of had this going down through the stack. And the next step is going to be open source silicon. So where will this lead? I think that's an interesting question. I think what Bunny Huang is doing with his secure hardware, he's using an FPGA there to prevent supply chain shenanigans. And open source silicon, I think, is maybe the ultimate way of protecting your security. We'll see unpredictable innovation with open source stuff, simpler, more accessible tools, and greater accessibility. So more availability. And part of the accessibility is the cost. So we'll see how that figures into things as well. So when I was getting ready with all of this stuff, it was really blowing my mind at what a crazy field this is. So it's full of huge and tiny numbers. So we've got like tiny feature sizes in the order of nanometers. So we've got meters 1,000 times smaller as millimeters, 1,000 times smaller as micrometers, or microns 1,000 times smaller than that is nanometers. And nanometers is the scale that we're operating on here. We've got huge setup costs, which is one of the things that's held it out of the approachability for makers, for example, or like the Hackaday community. The tiny switches used inside modern chips, MOSFETs, they are the most manufactured thing that has ever been made, 1.3 times 10 to the 22, according to Wikipedia, which is totally mind-blowing. And yeah, it's magical in a way. Computers think using etchings and poison sand and measure time using vibrating crystals. So if you're looking for magic, you found it. I like that quote. And my buddy, Niels Mosley, who helped me out with preparing for this and just discussing ASIC stuff, said that it was trying to do a 0 to ASIC workshop was mad, but in a good way. So that's kind of given me hope that it's worth doing something like this. When I first got into learning about VLSI, very large scale integrated circuits, I read this book and it was really interesting. It's quite dated in terms of the technology, but it's very refreshing in the way that everything's open. And one of the things that they talked about was about learning by doing. So that resonated with me, and I hope that resonates with you as well. And you see that throughout this this demo that there's nothing really unapproachable here. And with the announcement of the open source development kit from Skywater and the new tools that we have and the free Shuttle from Google, that actually this is something that is maybe possible for you to get one of your designs on silicon. That was certainly one of the things that really excited me as an electronic engineer for 10 or 15 years. I never really thought that I would ever make a chip, but that's always been kind of like I don't know, kind of magical thing for me, maybe. So a little bit of context. Digital computers need switches, and it used to be mechanics, and then it was relays, and then it was valves, and then it was transistors. And in transistors was the first transistor was 1954. This is the from the a photo from the Computer Science Museum in San Francisco. And then this is an integrated circuit. So when you put multiple switches together or multiple parts of a component on one bit of silicon, it becomes an integrated circuit. So it's a way of making things smaller. And we see over the years how things just got more and more and more exponentially complex. And now we've got millions or billions of transistors or switches on a chip. So I'll just play you a quick video here. This is, so we've got a chip here, and the top's been etched off, and you can see the gold bond wires that break out this little chip of silicon in the middle, with all the patterns actually do the magical work. And one interesting thing here is that this chip is so tiny that it has to be put in this big block of plastic and then bonded with these bond wires for us to actually get those signals out to the real world. And now we're switching from the optical microscope to the scanning electron microscope. We start to see some of the internal structure here. So these thicker lines here are going to be power distribution. And then we start to see all the fine interconnect wires that connects everything together. And then you can start to see underneath those tiny wires, we've got some other structures with some other wires, these slightly thicker ones. That's more power distribution. And then underneath that, we've actually got the switches, the MOSFETs. And this this dimension here, this is a critical dimension. And it's about 1,000 nanometers in this video. And that dimension in the toolkit that we've got from Skywater is about 150 nanometers, so even smaller than this. So a MOSFET is a type of transistor. So these small switches that we need to build up the chip, we use a MOSFET these days, which stands for metal oxide silicon field effect transistor, so quite a mouthful. First MOSFET is 1959, attributed to 2 people. If you've used MOSFETs in your own projects, maybe for driving motors or H-bridges, they the big ones look like this. I think actually this thing that I've got on my desk here is a MOSFET, is a smaller package. So we have a tiny little chip of silicon, and that on the cross section looks a bit like this, and then it's put into a bigger package, maybe to make it easier to solder or easier to dissipate heat. And if we look across the surface of the silicon, we have a structure a bit like this. And I'm not going to get too into this, but just a really super high level overview. The way I think of this is we have a capacitor formed between the gate and the body. So this oxide layer here, silicon dioxide, is non-conductive. Then we have a metal layer here and a metal layer here, and then this semiconductor here. So when you've got 2 metal plates that are insulated, you've got a capacitor. When we put an electric field across here, it changes the electrochemical properties of this channel region, and it allows a current to flow from the source to the drain, or the drain to source. And if you look at this picture, it's symmetrical at the moment. And we normally, to make these actually work, we make them asymmetrical. So you can see in the circuit symbol down here, there's an asymmetry. So I won't get into that, but it's an interesting part of how the structures actually work on the chips. And this gate length here, this distance between the source and the drain regions for the Skywater process that we have access to now, that's 150 nanometers. So that's the scale. So why MOSFETs? They're easy to manufacture in volume. We've got this super cool way of making hundreds and millions of them all in one go. It's easy to change the size, so you can make a big one for power switching, or tiny ones for calculation, digital computers. And it's become the basic building block of modern electronics. So let's have a look at how we could use a MOSFET to build one of the most basic structures of digital electronics, an inverter. So an inverter, if you're just drawing it out on paper, you draw it like this. We have a simple truth table. If you've got an in of 0, the out is 1. So let's have a look at that. If the gate of the MOSFET is 0, it's not turned on. This is an NMOS. So if this is not turned on, then the pull-up resistor here pulls this to be high. So we get the output high. If we turn on the input, now this starts conducting. So it shorts this to ground, and then the output becomes low. And one of the problems with NMOS, and so the introduction to VLSI book is all based on NMOS technology, but one of the problems is efficiency, because when this is pulled down, this resistor is always conducting, so it's always dissipating a tiny bit of heat, but because you've got millions of them in a chip, it makes a lot of heat. And we all know from our hot computers and hot phones that cooling is a problem. So what we do is we put an N and a P channel together so that the P replaces the pull-up resistor, so that when the P is turned on, it's pulled up, and when the N is turned on, it's pulled down. So putting the two together in this complementary style is called complementary MOSFET, or CMOS. And the big reason to do that is for efficiency. So how do you actually make a chip? Well, fundamentally, you draw squares that represent where metal or the silicon dioxide isolation, or where the doping, the N or the P type semiconductor needs to be. And it used to be done by hand. You can see these people here doing some cutting on some red tape there. But you could do it on anything. You could do it on Inkscape. And actually, my first tiny demo is in logo to G2S. I've got a little Python script, and it uses a GDS Pi library. We'll get onto GDS later. It opens a logo, rescales it, and then for each of the pixels, it just draws a rectangle using this GDS format, which is the format that we send to a factory, which is called a fab. So if I do make, that runs the script, and we get a custom bit of GDS here, and I can measure this and see that it's 40 microns. So I'm going to put this on one of my chips that I'm sending to fab if it gets past CRC, and we'll be in for a chance of the smallest Jolly Rancher. But you could draw it in Inkscape as you want. The fundamental thing is that you end up with stuff in a GDS2 file format, and that's what you send to the factory. Now, I made a mistake on my practice videos because I thought taping out was actually people taping things, but actually what it means is, my buddy Omer told me, is that when they took the tape reels out of the computers and carried them to the factory, you take the tape out, so you finish doing the work on it, and we still use that term now, tape out. So if you want to know more about how this stuff is actually done, then I really recommend Sam Zalouf's video from SuperCon, because he built up this process in his garage using a very small set of masks and a big process size. So a very quick walkthrough is you get your doped silicon, so a P-type silicon ready, you put photoresist on top of it, you bake it, and then you put a mask on it and expose it with ultraviolet light, which changes the photoresist. And then when you develop it, you can wash it and wash away the holes. And then you can do some process. So you've got this kind of pattern on top of the silicon. And then you can either etch and cut away, or you can bombard it with N or P type dopants to change the chemical structure of the silicon. Or you can grow a level of silicon dioxide on there as an insulation layer. Or you can grow polysilicon, which is another type of structure that we use on there, or put metal on there for interconnects. And you end up with these amazing 3D structures. So I just got this one straight out of Wikipedia. I quite like this one because it looks like out of a computer game. So if maybe someone wants to make a computer game 3D, you have to kind of jump and follow these bridges as part of the game. I think that would be quite cool. This is what an inverter looks like in the Skywater standard cell library. And I'll explain what that is in a minute. So the thing that I think that really piqued my interest on this is seeing how it's fundamentally a three-dimensional structure that builds up this functionality on the chip. And I saw this really recently on Twitter and asked permission to reproduce it here. And this is, you can see here, so this is like the working layer. So when I showed that MOSFET picture before, here's all the switches here, and then we've got all these interconnect layers building up. And this is like a reverse engineering process. So you can see how all these things are stacked up together that make up this whole working chip. Okay, so let's take for the next demo, let's take a quick look at how we would actually build a CMOS inverter using a tool. And the tool I'm going to use is Magic. And it's a very old tool, but it's still used a lot today, and it's used in the open source flow. So all of this stuff will be, this and all the slides will all be linked at the end, and you'll be able to download it all. So here's one I drew earlier. But I'll just show you now, if I wanted to make an N-channel MOSFET, what I need to do is draw where the N-type dopants are going to be implanted. And then I need to draw the gate. So that's made of polysilicon, middle click there. And then where they overlap, that forms an N-type transistor. At the moment, this is no good because it doesn't connect to anything. So what I can do is draw some local interconnect here and local interconnect here. And then at the moment, they're just on top of each other, but they're not connected. I need a kind of special via. So I need a N substrate, N contacts via for these two. Where is it? There. Now you see all this white stuff around here is Magic telling me that it's got DRC errors. So it's loaded with the Sky 130 process design kit, and part of that process design kit is the design rule check. So if anything is slightly overlapping in the wrong way or breaks a rule, Magic tells you what is the problem with these white areas. So you can see how you could build up a shape like this. And we've got the N channel here, the P channel here, the polysilicon gate, the input connector, the output connector. And then the way this structured bit at the bottom and the top makes this easy to duplicate and make arrays of and lay them out in big patterns. And that's what the OpenLane ASIC tool flow makes use of. So let me just quit this and start it again. Now, I know that this is quite small writing, but I'm going to show you something that I think is super cool. So because we've loaded the library and we've got access to all the models of all the transistors, what I can do is ask Magic. So I'm just typing in here, extract. And what that does is it looks at how everything is connected and then extracts a digital netlist. And then I can say X to Spice. LVS. That loads a whole bunch of defaults, but I don't actually want some of those defaults. I want to turn on modeling of the capacitance. So I've done that by typing X to Spice C/0. So whenever in engineering, we're always making compromises. Here, what we want is a perfect inverter, but we've seen that when they switch state, they waste a tiny bit of energy. And part of that is because we have a tiny bit of capacitance, this gate capacitance. So every time you change it, you have to charge up or discharge this gate. And that means that things aren't quite so fast, so they take a bit of energy, and that's the downside. And with electronic engineering, often these things are called parasitic. So we have parasitic capacitance. And what I've done here is turn on parasitic capacitance modeling in Magic. And then when I finally do X to Spice, it extracts all that out into a Spice file. And then I can do make sim, and that will run this through a simulation where I put a stepped input and output. So the red line is an input, and we've got 1.8 volts at the top here and 0 here. And then this is nanoseconds along here, 0 to 2 nanoseconds. So we've got the red going high and then it goes low, and we see the blue line following it. And if I right click and drag here, I get another one. And I can measure this and see that I've got 1 nanosecond. So by drawing the inverter and then extracting it, doing the model, I can see how fast these things can switch. And the other thing I wanted to show you was here's the current usage. So we can see with CMOS, the current only is used when we're changing state. And this is something that I've been doing electronics for a long time, but I never really thought about this before until I did this. So it was really interesting for me to realize that when you put your chips in low power mode, often what you're doing is doing clock gating. You turn off all the clocks, and then none of the logic can change state, and so your power doesn't get used. So yes, what's next? We've built an inverter and modeled it, but in reality, we're not going to be drawing all of this stuff out because it takes too long. And we might draw stuff out for analog side of things, but I'm concentrating on the digital side of things. So what we get from Skywater, and one of the exciting parts of this announcement was the Skywater 130 nanometer process has been made available on an open source license. And whereas previously you would need to sign an NDA to be able to use it, you wouldn't be able to publish your results. Now we can use this development kit, and it contains all the specifications of their process that they need, that they use to fabricate chips. It's called a PDK as part of the jargon. So we've already seen that we've got a DRC, the design rule check, so we can design stuff in Magic and know that it will work using their process. We have behavioral models, so that's what let me do the simulation, SPICE models. And we have this thing called standard cells. So I would never normally want to draw an inverter unless I'm learning. I would use a standard cell. So I can just show you now as another demo. This is using a tool called K-Layout, and here are all the standard cells for the high density version of the cell library. And there's about 150 of them. And here is inverter 1. So you can see it's quite similar to what I drew with the input and the output, and this top and bottom that all tile together. And I can measure this, and we've got 150 nanometers. So this is one of these critical dimensions. And we'll get a bit into why that matters and where the naming comes from in a minute. Let's take a look at an 8-way inverter. Shows new top. So this is put 8 of them all together in parallel, so we get much stronger drive strength. But you can see it's still the same. It fits. They're kind of like Legos. You can fit them all together in a structured block with power at the top and ground at the bottom. Always the same distance across the top. Okay. So standard cells. So a big part of the standard cell library is we've got all these cells. But also one of the things that's really confusing and made it hard for me to get started was just the density and the quantity of information. So if we go to this Skywater PDK, which I've got extracted here, I've got nearly 3 gig of files on disk. And if I find them all and count them, I've got 75,000 files. And a lot of this is not of any use to me at all, but sometimes I want to find a file or I need to look something up, and finding stuff in all of this is difficult. And that was one of the things that slowed me down at the beginning. Turns out you don't need that many things, but it's good to know where they are. So I showed you the high density standard cell library, and we've got 160 cells there. But we also have these different versions. I haven't got any of these on my computer, so I'm just focusing on the high density ones. But you've got ones that are optimized for high voltage or high speed or low power. Let me just check my notes. And have a drink of water from my beautiful bottle. So this is a not to scale look at Skywater 130 process that we've got available. So we've got the P substrate at the bottom. If we're drawing a P channel MOSFET, we need to insulate it with an N well. Then we have the diffusion layer. So that would be P for a P type or N for an N type. Then we've got the polysilicon gate. That was that red stuff that I showed you in Magic. The local interconnect that joins things up. Here, this kind of green layer, local interconnect. And then we've got a metal one. So underneath here, let me see if I turn on this pointer. Underneath this level here is all the standard cells. And then above on this is like a 4-layer circuit board that we get given kind of as part of the process design kit. So we can put all the standard cells in an array and then connect them all up in the way that we want with metal layers 5, 4, 3, and 2. So with the PDK that we've got from Skywater, we've got 33 layers. This lot are used for actually drawing the transistors. This lot is for connecting things up, and this lot here is for packaging. And I'll explain the packaging bit when we get to the shuttle at the end. Okay, so very quickly. So these slides come from Mohammed, who has been doing a lot of work on, and he did a presentation for the FOSSI dial-up. So that's linked in the resources at the end, but I just want to thank him for the slides. We've got a bunch of file formats. The GDS is the thing we send to the factory in the end. And we've got def and lef files, and they're used a lot in the intermediate processes. So the def files are just kind of, because we end up with millions of things, the computers can really slow down if you're trying to have all the information at once. So you abstract it by having just where the blocks are, the cells are, and where the inputs and outputs are. And then you forget everything else. So you can do the routing just with the def file. And then the lef file allows you to see what's inside that. So you would need to load both of those things together to actually make sense of the intermediate files. And I'll show you an example of that when we get onto the OpenLane ASIC flow. So I already mentioned DRC as part of the process development kit, process design kit. And I just wanted to share my favorite example of a DRC rule, which is an antenna rule. So remember, we're building up this structure layer by layer, and we start at the bottom by building our gate. And then we maybe connect it up to a metal 1, go through a via metal 2. But between every process, we need to kind of clean and flatten the wafer. And that cleaning process can charge up anything that's exposed. So this metal 2 could get charged up. And then if there's enough charge on there, it can destroy the gate. And we break our chip in the process of making it. So a DRC antenna rule is make sure that these metal lines don't get too long, or if they do get too long, that you have like a special diode here that protects the gate. So if you've ever done electronic engineering, you often have these special ESD diodes, electrostatic discharge diodes, that protect things if you touch them with a static shock. And we basically use a very analogous thing here to protect the gate against static shocks during the manufacturing process. So I mentioned this whole 130, Skywater 130 nanometers. This is another thing that I found really confusing and frustrating when I was getting involved. I was like, this 130's got to mean something. What does it measure? Is it like what part of the chip does it measure? But it doesn't anymore. It used to mean the gate length and the half pitch. Back in 1992, they were both the same. So they got called the 500 process, node 500. But as time has gone on, these numbers have drifted and they don't line up anymore. A recent IEEE article titled "The Node is Nonsense" was quite interesting. They were talking about better to choose something that tells you about the density of the cells that you can get on, or something that is more fundamental. But the structure, this Skywater 130 is using like a very traditional MOSFET structure, and the latest tinier ones are quite different to this. So this is a fairly old process, but it's still extremely useful. So this comes from Mohammed Qasim's presentation, also on FOSSI dial-up. And Europractice ASIC factory, 50% of their output is 130 nanometers or bigger. So it's still very widely used in industry. Okay, so we got on to OpenLane. So you can check out and download OpenLane from this GitHub link. And it takes in design files and then spits out GDS2 files with very, very little intermediary messing around that you need to do. It only takes about 15 or 20 minutes to install, but you will need about 3 gigabytes of space on your computer to get the PDK in there. So I'll just talk through this process briefly, and then I'll show you a couple of examples with showing the intermediate files so we can see how the GDS files that we're going to send to the factory get built up layer by layer. So we typically write a model of the thing that we're trying to design with a high-level language. I'll get onto that in a bit. And we need to synthesize that text language into a list of like ands and ors and flip-flops, these fundamental digital building blocks. We can do STA, static timing analysis. So that allows us to work out how fast the chip can work. And then design for test, DFT, allows us to put special structures in the chip that make it easier to debug if things go wrong later. Then inside we've got Open Road, which is a whole other toolkit that is like the kind of the core of this flow. And it does floor planning, which is working out how big the chip needs to be and where the pins go around the outside, where best to put the cells, clock tree synthesis. So the clock is usually our designs have a clock in them for digital design, and the clock is one of the most important signals, and it needs special consideration. Optimizing and routing, the antenna diodes insertion, so that takes care of the DRC rule that I explained about the antenna diodes to protect the gates of the MOSFETs. We can do a logical equivalence check, so that checks that the output from what we've got from Open Road matches our input. Coming on through here, we can extract the parasitic resistance and capacitance like I showed you in the Magic demo, and that can give us a better understanding of timing. We can do another timing analysis, and then we can do GDS2 files. So we can generate the GDS2 file, and then that's what we can send off to the factory. So I'm going to show you this with an example, continuing with the inverter example, because I want to take this inverter and show you all the way through the process. So like I said, we're not going to draw an inverter. We're going to use a standard cell, but we're not going to arrange those standard cells by hand. We're going to use a high-level language. And in this case, we're going to use Verilog, which is a hardware description language. And we can describe the hardware we want by typing it out in text. So I can say, I want a little block with an input and an output, and the output has got to be the NOT of the input, and that's all this is saying. And then I give this into the beginning of here, and it goes all the way through, and then out we're going to get the GDS2 files. So let's see how we do that with OpenLane. All right, so to start OpenLane, I have an alias called start OpenLane, which moves me to the right place and starts the Docker. So the way this is distributed is as a Docker. And if you don't understand that, it doesn't really mean anything at all. It just means that we're kind of running we're running the tools inside a virtual environment, which probably also doesn't help. And then on the other window, I'm going to be in OpenLane designs. So I'm going to say flow. So the main tool here is flow. And I'm going to say I want an inverter design, and I want to init design config. All right. No, not double slash, single slash. All right. And then here, I've got this setup file. I've got nothing in source, and I've got a default config. So this is all generated for us. Now I'm going to copy to save time, but show you. There's no magic here. Here's the same file I showed you on the screen. Make that a bit bigger. And then over here, I say flow design inverter, and that's going to run. And while that's running, I'm going to go back up here and show you this. So this is the output of YOSIS. So it's read that HDL and it's worked out that it needs an inverter and got an input and an output. And then I can also look at, after the mapping to the standard cell libraries, now it's chosen this Sky 130 high density inverter 8. And that was the one that I showed you with the 8 inverters in a row within it. So now we've got the actual standard cell that we need. Let's see how OpenFlow's gone. Okay, it's failed. So I knew this was going to fail. And this is very much part of the process here. So you're going to get a failure on something, and then you're going to have to try to work out. So what I do is ask my questions in the Slack channel, and then helpful people help me understand the errors. So what this is saying is that basically the design is too small. The default config works very well for normal designs, but actually this design is so small, it needs a couple of changes. So back in the inverter, let's edit the config file. And we need to change the density. And then I can run the tool again. And this time we're hopefully going to get a bit further. All right, let's take a look at the log. So this is the output from YOSIS. So it's telling us, okay, there's the standard cell it needs. Oh, and we've got another fail. And this time it's saying clock tree synthesis, CTS. So our design doesn't have a clock, so actually we need to turn off that. So again, this is something that you wouldn't need to do normally. There we go. So this inverter design is now part of the demos inside OpenLane. So you've got access to this. And here we're just saying there's no clock and don't bother about the clock port. Okay, so third time's a charm. Just as well, this is a super quick one. And we're getting a lot further here. And we've got a result. So back here in where the source is and the config, we've also got runs. So we've got the 3 runs that we just did. And this is the latest one. And there's a lot of intermediate files. And this is another thing that took me a long time to get my head around. What does all this stuff mean? What stuff to pay attention to? What stuff to ignore? So for now, all I'm going to show you is just the final result. And then for a slightly more complicated result, we'll take a look at a few steps along the way. So the way I'm going to do this is presentation tools, and I'm going to say make magic final design run date equals. So that little bit of stuff in the background there's what I'm using to make it fast for me to show the intermediate files in this presentation. And the make file is pushed on my GitHub, so you're free to check out what's actually happening there. It's not too hard, it's just to save time. So we've got our input here and our output. Zoom in a bit. And most of this is filler. We've got our power distribution here on these big vertical and horizontals. And then we've got thinner horizontals for the power and ground. And you can see here, this is where the standard cell fits in. And it's a def file at the moment. So we're not seeing any interior stuff to save cycles on the processor. But I can select that, press X, and then that shows me. So this is the same thing that we saw earlier. Zoom out. And then these things, all this decap, these are decoupling capacitors. So it's all basically full of decoupling capacitors. And this whole thing, if I type B and go here, this is telling me it's 20 microns by 20 microns. So absolutely tiny. We've got 10 million square microns to play with in the Google Shuttle. So let's now move on to describing circuits with hardware description language. So I started off with that with the inverter design. Now I want to show something a bit more complicated and then run that through the OpenLane flow and show the intermediate files, a few more steps. So we're trying to model hardware, and it's kind of split up into two things. We've got combinatorial circuits where you've got lots of AND and OR gates where as soon as you change the input, the output changes. And we've also got sequential circuits where the output doesn't change until you get a clock, and those are kind of built up with flip-flops. We've got various different options to use here. Verilog is probably the most common, especially in the States. And we've also got these kind of meta languages that are often Python libraries that generate Verilog for you. Yeah, there's a lot of choice here. I'm sticking with Verilog because it's the most well-known and the most well-supported. So let's make a slightly more complicated digital design. Let's make a 7-segment second counter. So we're going to have a 16 megahertz clock come in, and then we're going to build an ASIC. And when we put a 7-segment display on the back end of it, it's going to count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 to match the seconds. So inside the ASIC, we need something that can count up to 16 million. So every time this clock triggers 16 million times a second, we count it. And once that counter gets up to 16 million, we can send a trigger to a digit counter, and this will count from 0 to 9. And then we'll make something that takes that 0 to 9 and then decodes it into the segments that we need to have on our 7-segment display. And then we'll walk that through the whole OpenLane process. So same as before, we've got an input clock, input reset, and now we've got 7 wires coming output to drive the LEDs, 6 down to 0, so 6 including 0, 7. To count up to 16 million, we need 24 bits. So we need 24 flip-flops, and we can ask for 24 flip-flops to be wired in a row by saying we want a reg, so register 23 down to 0 second counter. And the same for a digit, but we only need to count up to 9. So we'd make that 4 bits, and we can count up to 16. This is to do a simulation, so I'm going to ignore that now. And then here we've got the sequential part, the counter. So this is saying that it's only going to trigger on the clock. We've got a bit of reset stuff here, so if we get the reset, set everything back to 0. Otherwise, if we hit the maximum counter on the this 16 million cycles per second counter, set that back to 0 and increment the digits by 1, and then do the same with digits. So if they get up to 9, set them back to 0. Otherwise, we're going to just be adding 1 to the second counter all the time till it gets up to 16 million. So it's very tempting to read this as C or something sequential, but it is absolutely not. It's one of the difficulties with a hardware description language is that you're describing hardware. So when I write something like this, I've basically told it that it needs to build a full adder out of digital logic so that we can add 1 to a register every time. And when I say something like this, I'm saying build a set of combinatorial logic that connects to each of the flip-flops in second counter that can do like a complicated add or XOR whatever until it gets to a single signal that goes high if it gets to 16 million and is low at all other times. And when I say register, what I'm asking for is a whole load of flip-flops all joined together in a way that lets me use them as a block of memory. Then down here, I've got the bit that does the 7-segment decoding. So this is combinatorial logic, one way of doing that. So whenever the input counter changes, so this is this number from 0 to 9, then it's going to be setting the segments to be what we need it. So let's take 3 as an example. If the input is 3, then we want segment 1, 2, 7, 3, and 4 to be on. So here was 7, 3. So 1, 2, 3, 4, and 7. So that's how it would show the 3 on the LED 7-segment display. So let's now run this through OpenLane. So I'm going to do flow design 7 segment seconds. Yeah, this takes a little bit longer. So now while that's running, I'll go to OpenLane design 7 segment seconds. So in source, I've got that same file. And config, this is the default config. So I didn't need to change anything for this design. So because it's big enough, all the defaults work fine. I didn't need to mess around with that. If things don't work and you need to explore the design space, then one of the cool things with OpenLane is it has these kind of feedback loops. So you can say, try with these different densities or these different clock speeds or these different aims for area, whatever you're trying to optimize. And it will go round and round in a circle, trying all these things out and then give you a report at the end of how well it's done. So we taken our design, this 7 segment seconds, and it's being synthesized with Yosis, as we've seen before. So this input Verilog has gotten turned now into this netlist. So let's take a look at that. Post-synth ... This is a much bigger file now. Let's see. So this part here is the comparison. So we've got the counter, and that we've got 24 elements of that bits, and you can see how they're all being NANDed together or ORed or all knotted all the way to the end until we get to this one last signal. That's going to be the rollover signal when it matches with 16 million and it increments. This is the full adder that can add 1. Here's all the D-type flip-flops that are used to store that number. So we've got a bunch up here and a bunch down there. I only know this as quickly as I do because I've spent some time looking at this diagram before I showed you. Here's the 4 D-type flip-flops that we need to store the numbers from 0 to 9. And then this is the decode logic. So this is all this combinatorial logic. So as soon as this number changes, it flows all the way through here. And then the output segments changed here. So let's see how that's gone. Right, it's finished. So now I'm going to go back to, okay, so got to do the same thing with runs. So the latest one is this one. And I'm going to show first the floor plan. So this is where the tool's trying to work out where things are going to go and putting the pins in. So there's very low detail. So make magic floor plan. Design equals 7 segment seconds. Run date equals. So down here, we've got all the standard cells that are being used in the design, loads, but they're all on top of each other. And then here we've got, let's just zoom in here. We've got the pins being laid out. And then the rest is kind of the basic structure of the size of the chip. Then we've got like a coarse and a fine placement. So all those standard cells are now going to be put in the right places. So I'm going to say magic replace. This is one of these intermediate files. So now things are kind of roughly in the right place, but they're not lined up on the grid. So we can't route them yet. You can see they're all kind of overlapping each other in not a great way. And then we'll look at the detailed version. So that is placement. And now everything is lined up. So they still look overlapping, but remember that the standard cells do overlap on the top and the bottom because they're sharing the power lines. But it's all very ordered now. And so the final step is wiring it all together. So that is Make Magic Final. So we've got the pins, got everything laid out. We've got quite a lot of filler, but we've also got all the juicy standard cells that are making this work. And as before, I can, let's find something like this one. This is a 3 inputs and gates. And I can do this and see because I've loaded the left file as well, I can bring up this extra detail and see inside. So how big is it? I can type B here. And this is 100 microns by 100 microns. And so that's 10,000 square microns. And we've got 10 million square microns. So we can put about 1,000 of these designs into the Google Shuttle. So that gives you a kind of a sense of scale about what you could achieve experimenting with this kind of stuff. Okay. Yeah, we've just seen this one. And then the sign off is done with layout versus. So, yeah, so if OpenLane finishes without an error, it's DRC clean and it's ready to send to the foundry. Although one thing we've not looked at yet is the pad ring, and that's the bit that the design fits into that has the bond pads that break out to the chip. So that's what we'll look at with the Google Shuttle. Which is the next but one thing. I just want to have a quick time check because I know people are going to go to, they're going to other workshops. So what is the time now? Nearly 11. So I think I've got time to talk about this as well. So we are making physical hardware here. We're not doing stuff with like a VeraBoard or a breadboard. We can't change stuff after it's been made. And we have this super long waiting period, maybe 2 or 3 months before we get our design back. So we want to be super, super sure that everything's going to work well. And we can do that with a combination of simulating the design. So that usually that's showing that some functions work. So in my 7 seconds, I can do make sim. This uses an open source simulation framework called CocoaDB. And then I can load up all the digital waveform here. So I can see the clock changing, the seconds counting up, the digits changing, and then the decoder working. You can use a coverage tool, and that tells you how much of your design you're simulating. And that can tell you whether you're missing stuff. And you can do verification. So that's like one of the options for verification. We've now also got open source formal verification tools, which if you've seen any of my other videos about that, you'll know what that's about. But that's a way of proving that your design is good and is going to work. And that's a way of saving time and cost with this kind of stuff. So final chapter. Thanks for bearing with me on this super long demo prez, is the Google Skywater Shuttle. So I don't know why it's called a shuttle, but I thought I'd put a fun space picture in here. But essentially what it means is every few months, one of these big factories takes like a group order, and that's called a multi-project wafer. So instead of like just one factory, like one design company, like say Texas Instruments buys like 1 million wafers or whatever, they a whole group of people team together and buy a little slice on a multi-project wafer. So you send your designs in, they're all aggregated onto one, and then that wafer is made and then it's sliced up and it gets sent out to everybody. So when I was first looking into this a couple months before the announcement, it was looking like it was going to be kind of $10,000 to $15,000 to be part of a multi-project wafer. And one of the exciting things that has happened recently is Google have made a free shuttle. So by putting your designs in an open source format and submitting them to eFabless, you can have a chance of having your silicon made. So this is from Tim Ansel's slides, again on the FOSSI dial-up, kind of explaining the philosophy. Your design has to be open source. There's about 40 slots, and then each of those slots is going to get about 100 or 150 chips back. The first run is soon, so end of November. That's the current date, although we're still waiting on a few critical things like the pad ring and the I/O pads. That's being done right at the moment, right now. And that's going to happen every quarter if there's enough demand. So I hope one of the outcomes of this demo is that people get involved and make sure that there is a demand, and that will make sure that there's more of these shuttles running in the future. So let's have a quick look at the harness. So your design is going to go in this mega project area. So this started out as 10 square millimeters, so about 3 by 3 millimeters. But it's shrunk down a little bit by now. But when I was doing the calculations and sorting out this presentation, it was a bit bigger. And then there's like a whole bunch of support circuitry. And the idea here is a way of kind of supporting, giving common support for your designs. So we've got a RISC-V processor on there, some RAM, some I/O, ability to read programs off the flash. We've got a logic analyzer built in, a wishbone bus, a whole bunch of support stuff. So if you add like this design for testing, we can like read in or set things using the RISC-V processor. And then this is where your design is going to go. And then all of that's going to be packaged on a wafer level chip scale package. So when I was looking into this, I was thinking it'd be cool to get one of these big kind of ceramic dual inline packages, but they are really expensive. You pay like 10,000 euros for the MPW and then 5,000 euros for the packaging. Whereas this is all done in the fab. So it's kind of much cheaper. And those final 5 layers in the Skywater PDK layers are these layers here. So the back of the package is actually the back of the silicon wafer. So it's really thin, really small. And then we've got, it's a bit like a BGA package, ball grid array. So we've got the bumps on there. So it's a trade-off. It's cheaper and it gives better performance. There's lower inductance because there's no bond wires. So it's good for high-speed designs, but it's a little bit harder to solder. Although I find BGA easier than QFN personally. So, and you're going to get about 150 of these. So if you mess up a few, it doesn't matter. So I think this is the ultimate slide. This is just like showing you some designs. So the Pico RV32 is kind of like a common RISC-V processor made by my friend Claire. And you can fit 10 of those on that mega project area. You can fit 10 USB endpoints. You can fit 10 AES encryption cores. You can fit 8 IBIX RISC-V cores. You can fit 1,000 of those 7-segment decoder little blocks that I made. This little VGA clock that is going to be one of my first designs. I think I can get about 500 or 600 of them in that mega project area. So here's all the resources. Go to the slides. Here's the slides. Then you can click on all the links. The FOSSI Foundation dial-ups are really useful. If you're going to take this seriously, get involved in the Slack. Kunal's Udemy course, the VLSI one is a good one for like getting started, and this Introduction to VLSI books is good. I'd really recommend simulating and making your design work on an FPGA as well before trying to go to an ASIC. That will really help you with your digital design. I'd like to recommend Tiny FPGA and Icebreaker, and what the FPGA course as a way of getting started. And then my repos that I've used for this presentation are all here. So big list of people to say thanks to. Really helpful getting me up to started, helping me proof the presentation, telling me what stuff is too crazy, what stuff is not crazy enough. And then the final thing is, if you're interested in doing this, I'm going to be running a paid course later. So if you're interested in paying to do like a 10-hour Zoom course, where at the end we multi-project wafer on the multi-project wafer, put all our designs in this area and then send that off as part of the application for this ASIC. Show me your interest here, tell me what you're interested in learning, give me your email address and I'll keep you up to date with that. So that's the end of the presentation. Thanks very much for your patience. And I'm going to bring on Mohammed Kasim now to help me answer questions and give me a break so I can get a little drink of water. So
Hello.
Stop the screen sharing. Hey, Mohammed.
Hello. Hello, Matt
Hello,
and
new
everyone.
gallery view, so you're on there as well. So I'm on Twitter, not Twitter here, Twitch. So if people got questions, feel free to just bang them in the Twitch chat. And if there's anything I can't answer, then Mohammed will surely be able to. Oh, good. Got a shout out from Horizontal. Thanks, Mine. And thanks, El Viejo Adi, for putting the link in there. Verilog or VHDL, yeah, that reminds me of the slide from the last Hackaday SuperCon with the badge, and Sprite TM said the VHDL stands for Very Hard Difficult Language. So VHDL is getting supported, but is not very well supported yet, I would say. So Verilog is still the one to be going for. Like high level, yeah, got a juggle. What was the hardest thing while you were learning? I think, yeah, just getting like, yeah, it's so deep. There's so much technical jargon. That was one of the big reasons why I wanted to do this, was to try to unpack everything. And then I heard a really good podcast called Ologies, and it had Bill Nye, the science guy, on it. And he said about how you should never introduce terminology and then explain it. You should explain the thing and then say, here's what it is. So that's like what I tried to do with saying, as a way of making NMOS more efficient, you put two MOSFETs together and then they become complementary. And that's what CMOS stands for. Hopefully that makes things easier to understand. So yeah, I think probably getting over the jargon. Like for ages, I thought I've got to find out what this 130 nanometer stands for. That was really annoying. Have you got an opinion on that, Mohammed?
Yeah, it's the transistor minimum transistor feature in length. So the logic transistor in this process is 0.13 micron minimum. And
but it's not always that, is it? Like at the moment we've got Intel and Taiwan.
Yeah, so this has evolved. So it was started in two microns, 1 micron. So there's an evolution across the time from very large transistors all the way to now, as you can hear, 3, 5, and 3 nanometers. The technology, as you get down beyond that, maybe 20, you start getting the optics to start to be crazy. So there is a lot of investment to actually make it work at this length. And that means you can get the transistor as short as 130.
Mohammed, there's a question here that I think you'd be the best person to answer, which was, where are we at with the IOs? How are the IOs handled?
So the IOs are actually, right now, the IOs are finished. They have not been released yet, but they have been finished. At least the set that is associated with the harness, it's out there. It's going to be out there soon. Meaning soon, hopefully tomorrow, because I know Tim Ansel and the team has been working on it today. And so one of the things that I want to mention, if you're going on the shuttle and you have a design, you will not need necessarily to play with the IOs. If you're building your own design that is completely from scratch, you will, of course. So just if you case for the shuttle, we're asking people to focus on the box, and we're actually probably releasing in a couple of days a new version of the design that has a little bit more area for the user space at the expense of other area as functions that we didn't want to have on the rest of the chip. So stay tuned for that.
Okay, I've got a few more questions. What analog blocks are available in the PDK, PLLs, level shifters, etc.? Yeah, I've not actually looked at any of that. So Mohammed, over to you.
So the PDK that is released, is the PDK lowest level. It is the transistors and components and the standard cell digital libraries, 4 or 5 variants, I don't remember, and the IOs. And this is it. So there is a vacuum of analog, and I'm counting on the community and that we actually identify a list and go through a target one by one and make them open source. So power management related, clocking like PLLs. And these, in my opinion, I saw, I always see somebody talking about the high-speed interfaces and SerDes, and I say we don't even have an amplifier yet, open source. So I encourage the community to go do that and help building that library very quickly. Well, I'm not saying just stop at the amplifier, just the general next level components beyond the transistors.
So one question for me was, what design am I working for the my first application? So I showed this like little VGA clock, which is, well, I just pulled the power out. I'm going to put, I've got a few other people that I've been working with who are putting their own designs in. So there's going to be a frequency counter, something like an SPI multiplexer that someone's using for a Raspberry Pi cluster. I'll definitely put a little Hackaday logo in there. Yeah, I'll probably try to put maybe 4 or 5 or 6 things in because there's so much room. People are also talking about trying stuff on an FPGA first, so I would definitely agree with that. Simulation can take you a long way, and verification, but sometimes you get this mismatch between the simulation and what is actually happening. Like you get these weird metastability or clock domain crossing problems that are not trivial to solve, and they can show up on real hardware. So running stuff on an FPGA can give you a little bit of an insight whether that's going to be a problem.
Yeah, I saw a question here about whether Magic is capable of parasitic extraction. The answer is yes, and there's also another effort going on K layout to add the extraction rules for it.
And what about an open source FPGA? Yeah, that's in progress. That is, do you know if that's going to be in the first? Is that going to be ready?
Well, from the laws of statistics, we have 4 different people working on different things or different activities. So they're gonna, one of them is hopefully gonna make it. Yeah, but I think they're gonna make a few of them different architectures. Some of them are tried before and some not. So, but there will be a few slots filled with an eFPGA.
Are they going to make their own like standard cells for FPGAs? Like, are they building a lookup?
No, no. So this is actually the easiest and the most flexible approach that was used for targeting the process is to build the FPGA itself from the standard cell library. So literally, basically, it becomes a digital design with a certain regularity, and you put it together, and it becomes an FPGA. So it actually makes it. Sometimes you need to make a custom cell for certain footprints that don't exist in the standard cell, especially if the design is high density. But generally speaking, the open FPGA project is based on standard cell based architectures.
We've got another question for you here about, are the Sonos cells available?
Nope, they are completely proprietary, and they're not at this point open source.
What are Sonos cells?
It's a technology that Cypress has developed from memory and other, and then they're not going to be there. So it was not part of it.
It's like a proprietary technology made by a.
Well, it was not made open source in the context of this project.
Okay, are there any active open source projects for tiny microcontrollers, 8-bit or below? 8-bit or below? I think, I mean, Pico RV32 is like the classic RISC-V small one. That's a 32.
32.
Only implements the the smallest part of RISC-V. I mean, there's a lot out there, but that's like that's been taped out 10, 15, 20 times. It's used quite a lot, isn't it?
Yeah, we've, at least on our side, about 5 times. So I think actually as far as tiny microcontrollers, I will not claim that is their effort, because I don't know. Here's the beauty of open source, is that you don't know who's doing what where. So sometimes when they evolve it to a certain maturity, they show up. But I have been personally seen efforts there, and if they make sense, then people should do it.
Yeah, also, I should signpost your talk on FOSSI dial-up, where you introduced the Strive series, because those are like small general purpose.
Yeah, and they are based on the Pico RV32.
We've got a question here. What kind of DFT design for test OpenLane is going to use? Scan chain? So we're going to have like...
Yeah, so actually, and I need to check whether this is already released or not, but we're there's an open source engine called Fault. It has the scan chain insertion and vector generation, and it wasn't available in the first time around when we put out the OpenLane. Now it will be in the upcoming one.
Here's an interesting one. Can standard cells be drawn by other shapes other than rectangles?
As long as you follow the design rules for manufacturability, generally yes. However, in the design rules, there are layers of criticality. Some of them are manufacturing rules that are hard rules that if you don't meet them, you get a failure, or short circuits or things like that. There are other rules that are potentially waivable, so that you can do more. You become more flexible to violate the first level. However, in general, at the standard cell, you can actually build the standard cell without violating a rule in any shape.
And if you've loaded the DRC inside, say, Magic, and you've loaded your GDS file in Magic, then it will tell you if you've got a DRC problem there, won't it?
Yeah, and then part of that actually is we, instead of loading into Magic with where you suffer from the display refresh and in the different layers, we also wrote a few wrappers around Magic and potentially around key layout for inline DRC would give you a report.
Or with Tickle.
Yeah. Well, it's just a wrapper around what Magic is doing, and that applies to extraction as well.
Okay, here's one for you, Mohammed. Do you guys have inverters with shifted thresholds in your library?
So I'm gonna admit shifted threshold.
I don't know what that means personally.
Yeah, I don't know what that means. It's either a second threshold, different threshold voltages, or maybe it's the threshold that is modified with pocket implants so you can reduce leakage. So,
I mean, there's the high voltage standard cell library, right?
that's, well, I just saw the comment here. So the high voltage standard library exists, but shifted, I don't know if you're talking about level shifted, level shifters. Yeah, I thought you're talking about threshold voltage, but level shifters, yes. And some of the IOs have, so because the IOs are tolerant all the way to 5 volts, 5 point something volts.
That'll make it easy to do breakout boards. Yeah, I'm really looking forward to having a little PCB with a plug-in oscillator and a few PMODs and this little ASIC in the middle. It's going to be super cool.
We're all looking forward to it. It's very exciting. Yeah, it's very exciting. Yeah, it's never.
So we're looking like we're on track for end of November for the first shuttle.
Yes.
So let's say that my submission gets accepted on that. When do I get the chips back?
So from typically, I mean, there's a window of 76 days just to get wafer out. So not packaged, not, and so there's a little bit of lead time on as well. So 76 days is roughly 2.5 months, right? So you're talking about February, maybe early March, packaged.
Fantastic, in time for my birthday.
Good. Yeah, I'm reading if there are other questions.
Ratboy saying, for hobbyists, after Google Shuttle prototypes happen, what's next? But I think maybe you think, maybe I've given the impression that there's just going to be one free shuttle, but as far as I know, and Mithro's in the comments as well, but as far as I know, there's going to be multiple shuttles. So if you don't make it on the first one, you hopefully make it on the second one.
Yeah, and one of the interesting sides is that there are the foundries, and generally they offer for some specific designs when the business need matches what is being designed, but we wouldn't depend on that 100% because you don't know whether that's going to align or not. But if you actually do something, our experience is something that potentially goes into the foundries library as an advantage, as a competitive advantage, then they would help you prototype it so that they can improve it and put it in their library, and they also make it as an available part of their portfolio.
So the clarification is you've proved that your design works on the shuttle, and then you want to scale it. So I guess the answer there would be you have a chat with yourself at eFabless. Like if you wanted to now make an order for 10,000.
Well, any scale that for this one, we need to be, it's going to be very clear. It's a certain number of units, right? And if the design Caravelle, the carrier chip, as well as the design, and it becomes of course, yes, this becomes will be the interface to the foundry.
Okay, so I think we're going to have just like a couple more questions because I want to be off the air in time for people to get to the workshops. another one from PDP7, Drew. Hi, Drew. We didn't have that chat, but let's do it soon. What process node would be needed for RISC-V 64GC implementation like Rocket or Ariane? I think that you could use this. There'd be nothing to stop you from using this process. I mean, you would want to run it through OpenLane and find out how big it is. But if you can fit 10 Pico RV32s in, you've probably got room for a bigger processor. Have you tried 64-bit RISC through OpenLane, Mohammed?
Well, the process is, well, there's a process and there's the flow. So the process, yes, I mentioned before, this has been used more than 15 years ago in high-speed processors, but they weren't. Now the flow itself, maybe I need to check whether the team has tried it on one of them or not, but it's I don't see a reason why not. We with OpenLane,
thinking area, like, is that
I don't know. It depends on how. If you want to know whether it's going to fit in the user space in Caravelle, then the only way to do it is to do it, and basically try different configurations and see how much you can get.
So Drew, download OpenLane, put it in, run the tools, and then look at.
And as far as the gate count, we were able to get all the way to like a 900,000 gates of course, a design that we made it just in a way, but it's because it's not exactly an architected design. The results may be different for different architectures being synthesized.
Okay, so last one, I just try to address one from Tommy Thorne saying RISC-V 64 without caches isn't that interesting, because I just want to say that one of the other FOSSI dial-ups was about Open RAM. So there's a different process for building big memories that uses a more efficient, in terms of area, process. So definitely check that out. So I think this is the sign-off time. So I just want to say thanks to Mohammed for helping me out at the end here. I really appreciate you being on hand to answer any questions I couldn't do. Thanks everyone for staying tuned for a whole hour and a bit. I know it's super long. I hope it was interesting, and hopefully I'll see some of you on a Zoom course near you. Ching.
Great. Thanks, Matt and Mohammed. It's been a pleasure having you today. I guess we'll see everyone in the next one.
Okay.